The next section of the chapter is average speed and velocity. So now we know the position, distance and displacement. So the next step in describing motion is to consider how rapidly an object moves. Average speed describes how rapidly the object moves, defined in the rate of motion. It is simply the distance over elapsed time. Since distance and time are positive, average speed is always positive. Again, the distance is a scalar quantity. Because of that, average speed is also a scalar quantity. And the SI units of speed is meters per second, because the SI unit of distance is in meter and the time in second. So the SI unit of average speed is meters per second, or ms minus 1. Now let's look into an example. Suppose a dog trots back to its owner with an average speed of 1.40 meters per second from a distance of 2.3 meters. And we are asked to find the time it takes for the dog to reach its owner. It's always easier to picture the problem to get a rough idea of the problem. So there's the dog and its owner. So the dog is at a distance of 2.3 meters. So if we note down the known parameters, distance d is equal to 2.3 meter. And the dog's velocity is v, it is equal to 1.40 meters per second. These are the two quantities that we have been given. And now we know the equation for the average speed. It is distance over time. Now we have asked to find the time. So by rearranging this equation, we can find the time is equal to distance over the speed. And now we just have to substitute the numerical values given. So the distance is in 2.3 meters and the speed is 1.40 meters per second. So the answer is 1.6 seconds. Meter cancels and the time is 1.6 seconds. So you can notice that here the distance has two significant figures and the speed has three significant figures. So the answer should have only two significant figures according to our significant figure rules. Let's see one more example. Suppose the dog trots with an average speed of 1.44 meters per second for 1.9 seconds. Now what is the distance it covers? So we have the same kind of problem and the picture is same. And check the known parameters. Now we have given the speed 1.44 meters per second and the time 1.9 seconds. Now we have the same equation, which is average speed is equal to distance over time. Now we are asked to find the distance d. So for that we can rearrange the equation so that distance is equal to speed over the speed times the time. Again, by substituting the numerical values, we can find the distance is equal to average speed, which is 1.44 meters per second, and the time is 1.9 seconds, which is equal to 2.7 meters. Again, the answer should have only two significant figures because the time has only two significant figures and the speed has three significant figures. So the answer should contain the least amount of significant figures. One more example. You drive 4.00 miles at 30.0 miles per hour and then another 4.00 miles at 50.0 miles per hour. So the question is your average speed for the 8.00 miles trip greater than, less than or equal to 40.0 miles per hour? First we will picture the problem. So the first 4.00 miles, the speed is 30.0, and for the second 4.00 miles, the speed is 50.0 miles per hour. So we need to find the average speed of this trip of 8 miles. Now how do we find the answer? So we have given the distances d1, which is 4.00 miles, speed is 30.0 miles per hour, and the second distance is again 4.00 miles with a velocity speed of 50.0 miles per hour. And we have only one equation for the speed. It is distance over elapsed time. To calculate the average speed, we need to find the total distance traveled and the total elapsed time. So the total distance is simply the 4.0 miles plus the 4.00 miles plus 4.00 miles, which is equal to 8.00 miles. To calculate the total elapsed time, we need to find the elapsed time for each distance separately. So elapsed time on the first 4.0 miles is, we can take it as t1. It is equal to distance over average speed. Now the distance is 4.00 miles d1 and v1 is 30.0 miles per hour, and we are getting 0.133 hours. So both the numbers has 3 significant figures, so the answer is in 3 significant figures. Now the elapsed time on the second 4.00 miles. Again the T2 is distance over average speed, which is equal to 4.00 miles over 50.0 miles per hour. Therefore the answer is 0.0800 hours. So the answer is in 3 significant figures. Only the trailing zeros counts. Therefore the total elapsed time for the entire trip is T1 plus T2, that is 0.133 hours plus 0.0800 hours, which is equal to 0.213 hours. Now we can find the average speed for the entire trip, which is equal to distance over elapsed time, and we found that total distance is 8.00 miles and the time is 0.213 hours. It is equal to 8.00 miles over 0.213 hours, which is equal to 37.6 miles per hour. So this value is less than 40.0 miles per hour. So because of that, the answer is the average speed is less than 40.0 miles per hour. So in contrast to speed, velocity describes the rate of motion as well as the direction of the moving object. So the speed only describes the rate of motion, not the direction. But velocity describes both the speed and the direction. So we learned that average speed is distance over time. Similarly, average velocity is displacement over time. So the displacement is a vector. So in symbolic notation, we write it as VAV. AV is average, which is equal to delta x over delta t. The displacement is final position minus initial position, and delta t is Tf minus Ti. So in here, if the final position is greater than the initial position, then velocity is positive. And if the final position is less than the initial position, the velocity is negative. Therefore, the average velocity can be positive, negative, depending on the traveling direction. And since the displacement is a vector quantity, average velocity is also a vector quantity, and the direction is given by its sign. Again, the SI units is in meters per second because the displacement is in meters and time is in seconds. So we can write it as meters per second or ms minus 1. Now let's look at an example of average velocity. An athlete sprints in a straight line for 50.0 meters in 8.00 seconds and then walks slowly back to the starting line in 40.0 seconds. So if the sprint direction is taken to be positive, we are asked to find the average sprint velocity, average walking velocity, and the average velocity for the complete round trip, and average speed for the complete round trip. Before solving, let's picture the problem. The athlete first sprint in a straight line for 50.0 meters in 8.0 seconds and then walks back to its starting line in 40.0 seconds. Now let's mark the known parameters. So the sprint distance is final position minus initial position. Here S is sprint, F means final and I means initial. So the final position is at 50.0 meters. Initial position is at 0. So the sprint distance is 50.0 meters. And the walking distance is, walking means W. So when he returns back to its origin, the final position is at 0 and the initial position is at 50.0 meters. So the walking distance is minus 50.0 meters. Now the sprint time, the first sprint time is final minus initial, which is 8.00 seconds minus 0. It is equal to 8.00 seconds. And the walking time is total time is 48.0 second and minus 8.0 second for the sprint time. Because of that, we get walk-in time as 40.0 seconds. Actually, the value is given in the problem itself. Now we know the equation for the velocity, which is displacement over elapsed time, or delta x over delta t. So these are the known parameters of the problem. Now in part A, we are asked to find the average sprint velocity. So sprint velocity is again the displacement over time. So we found the sprint distance here, delta x is, which is 50.0 meters, and sprint time, which is 8.00 seconds. From this we get 6.25 meters per second. The answer has three significant figures because both the distance and the time has three significant figures. So in part B, we have to find the average walk-in velocity. For that, walk-in velocity is equal to walk-in displacement times over the time. So we found the walk-in distance, which is equal to minus 50.0 meters, and the time is equal to 40.0 seconds. So the answer is minus 1.25 meters per second. The value is negative because it is opposite to the positive x direction. Now we need to find the average velocity for the complete round trip. So for the round trip, we need to find the delta x, which is final position minus the initial position. So here final position is at the origin, and again the initial position is at the origin. So because of that, delta x is equal to 0. And delta t is equal to final time minus the initial time. The total time is 48.0 seconds. That is the final, and initially it starts at 0. So delta t is equal to 48.0 seconds. Because of that, delta v is equal to delta x over delta t. So x is 0 and delta t is 48.0 seconds, so it is 0. Now finally we need to find the average speed for the complete round trip. And for the round trip, the total distance traveled, it is not 0, it is 50.0 meters in the positive x direction, and again when it is going back, another 50.0 meters. So the total distance is 100.0 meters, and the total time elapsed is, for the first 50 meters it is 40.0 seconds. For the first 50 meters it is 8.00 seconds, and the second 50 meters it is 40.0 seconds. So because of that, total time is 48.0 seconds. Now we can find the average speed, which is distance over time, which is 100.0 meters over 48.0 seconds. So the answer is 2.08 meters per second. Again, the distance has 4 significant figures, time has only 3 significant figures. Because of that, the answer should have the least number of significant figures, which is 3. Because of that, the answer is 2.08 meters per second. So let's move to the next part. It is often useful to visualize a particle motion by sketching its position as a function of time. For example, suppose a particle moves back and forth along the x-axis with the position and time listed in this table. There are two ways to visualize this one-dimensional motion. This figure A represents the plot of position plotted for different times. So we know that at t equals 0, the position is at 1 meter. So we can mark at t equals 0, position is at 1 meter. So this is 1 meter at t equals 0. And then at t equals 1, it is at 3 meters. So it is at 3 meters at 1. And again at 2 seconds, it is at 4 meter. And again at 3 seconds, it's at 2 meter. And at 4 seconds, it's at minus 1 meter. So we can represent the particle's path as in this motion. But this way of showing a particle's motions is a bit messy. Because of that, we replot this same information with a different type of graph. So this time the vertical axis represents the position x and the horizontal axis represents the time t. This type of graph is referred to as x versus t graph, and it makes much easier to visualize the particle motion. So at t equals 0, it is at 1 meter, and t equals 1, it is at 3, t equals 2, it is at 4 meter, again at t equals 3 meters, it is at 2, again t equals 4 seconds, it is at minus 1. So this way, it is easier to visualize the particle's motion. So this type of graph we call as x versus t graph. Now an x versus t plots leads to a particularly useful interpretation of average velocity. Let's find the average velocity of the particle in figure A from t equals 0 to t equals 3. From the definition of average velocity, V average is equal to delta x over delta t. So from our previous table, we know that delta x is equal to 2 meters minus 1 meter, and delta t is 3 seconds minus 0. So the answer is positive 0.3 meters per second. We can find this value from the x versus t plot also. If we draw a straight line connecting the time t0 and connecting the time t3, the straight line is AB. From the slope of this straight line, we can find the average velocity. The slope is y versus x. So y is delta x, x is delta t. So from the slope, we can find the average velocity. Therefore, the slope of a line connecting 2 points on a x versus t plot is equal to the average velocity during that time interval. It is a very important interpretation from a x versus t plot.